Okay, welcome back. In this video, we're getting to something of my own personal interest, which is porosity analysis of additively manufactured metal. So it's an example to demonstrate some functionality in Dragonfly. Let me start off by just creating a new session, and I don't want to save anything, so that's how you do that. Keeping in mind this video series is really just to show you how to do things and where the functions are for that. So at the moment, what I want to do is I want to load a session, which I've saved before, small cube session. This is down sampled data, which is it's making the demo easier. I've actually already registered the data, turned it upright, not actually registered it. As you'll see, well, actually I did register it. If you look at the coordinate axis, it's the Z axis is the bottom of the sample. Actually, just before we start, let's click on this object and refresh our memory how to get a nicer visualization. Use one of these presets. That's quite nice already. And we can change the lighting a little bit. Maybe just do that to make it a bit brighter. Maybe the background is not really helping that much. Let's not mess around with lighting and so on. The aim of this video is to do a porosity analysis. So what I'm going to do is we're going to start off with some basic segmentation tools. And where that is, that's under the segment tab. You see there main, we've been working on the main tab here. The segment tab is when you start to color in your data. So the main thresholding functions are found here. The define range is the most widely used one. The define range button, when you click it, shows a preview of lower or upper Otsu. Otsu is a thresholding, almost like ISO 50. So it means it takes the main two peaks in the histogram and basically finds the midway between those two. But the Otsu is slightly more advanced than just the midpoint. So it's slightly better in most cases, and it's very widely used. You can also use your own. You can calculate from the histogram. You can show the histogram there. You can export the histogram, and you can find the exact values of the peaks. You can then go and like that's on the main tab actually, and then on this you can then go and select your threshold value that you want. If you want to use 35,000, you can do that, and that's selecting more of the at the moment material. You can also just drag it manually, and so you can select anything like that. What we want to do is, in this case, let me just think, what do there's different things I want to demonstrate. We want to segment the pores in a good way. So the way that I've done it previously, I want to reproduce that here in Dragonfly using a simple thresholding method, which is reliable. Let's choose upper Otsu to define. At the same time, I'm going to demonstrate some thresholding or some segmentation tools. So let's choose upper Otsu, just the plain upper Otsu. I'm adding this to a new region of interest. So this is our first region of interest that we're defining. We have to remember to put off this preview button. So now we see the green of this region of interest. Now we see we've got the metal pixels segmented and the metal voxels segmented. And what I actually want to do is I want to I want to fill in this. So I want this region of interest to be the entire cube, including pores. We might want to do that to calculate the porosity volume compared to the total before only doing any fancy pore by pore analysis. So for this, there's a very nice way to fill inner areas 3D. You see this operation here. So if we apply that, it's working on filling in all these enclosed cavities. So I'm going to demonstrate a couple of things here. It's a nice, simple example to demonstrate, but keep in mind, we don't have to do all of everything I'm doing here just to make a porosity analysis. So this is now the cube total. So this is the entire cube. There's also, I know from looking at the data before, there's some exterior particles like that. You can see that over there. That, for example, over there. To get rid of that is quite nice. We right-click on this region of interest and we refine region of interest and process islands. So process islands are functions which allow to easily clean up a region of interest. In this case, we want to keep the largest region of interest. So we click on this keep by largest, and there's different options there. The 6 and 26 is basically how closely connected things are. If you choose 6 connected, that means they are connected only when they are touching voxel to voxel faces. There are 6 faces of a voxel, of a voxel cube, and the 26 connected means they are even connected when they are only connected by edges and corners of cubes. You don't need to know all of that, but that's when you become more advanced, you might use that. So you want to keep only the largest, and you see that one's gone there. So now we have only the cube there, and it's filled in. So this is the cube total. So I actually want to keep this region of interest for future use. So what I want to do is I want to make a copy of this, and I'll just keep that copy there. So now we're going to work further on this, and we're going to make an dilate function. So in this case, I'm going to dilate twice. And what you see is we're having now slightly around the sides, also some pixels. The reason I'm doing that is because of the next step. I'm going to now separate this region of interest into 2 with a shortcut. And the way to do what I'm going to do there is I'm going to split at Otsu for this region of interest. So what we do now is we've now got foreground and background. Foreground is the metal and background is the pores and the thin shell of air around it. So at the same time, I'm showing you some shortcuts which you might not usually have known about or found easily. So what we have now is we put the cube total off. This is actually not anymore cube total. This is cube total plus some air around the side. If we now have the cube background, in this case, we again can now refine region of interest. And now we can, all the shell of air around the outside would be quite a large volume. So we can remove by largest. And that's quite nice. Now we have only the pores on the inside. So this is now actually the pores, and we don't need that one. We can delete that one, and we've now got a nice segmentation of the pores. If we want to go back to the main tab and just demonstrate the, where are we here? I just want to contrast a little bit. So this is the contrast shortcut using that. And get out of that state with the escape button. So now we have these pores, the volume of the pores and the volume of the total might be different or are different. So if we click on the total cube and we compare it with the pores, we see that the porosity segmented here is 4.7%. This is how you do a quick volume fraction measurement. If we want to now analyze this porosity in more detail, we can, I just wanted to think there was something else I wanted to demonstrate. I think that's fine for now. We've got the pores segmented. You could also do it in a different way. Let's go back a step. We take the cube total like this, or even just we go to regular segment tab. If we now make define range lower Otsu, we can add that to a new region. This is the Otsu porosity. and we can click to define range off again. In this case, we've got Otsu porosity, and the outside air can be removed. So let's do that. Refine region of interest, process islands, remove by largest. Where is it? There it is. And now we have the Otsu pores. So if we put the regular porosity and the Otsu porosity on, you see that the method that I initially demonstrated, the first method, is actually highlighting more of those little black spots. So those are two ways to do it, the two methods. If we use my original method, what we do have is we might have some which are only comprising of 1 or 2 voxels, which we don't want. So again, we can refine region of interest, process islands, and remove by voxel count. So in this case, we want voxels to be at least 9 voxels, to comprise at least anything less than 8. Anything less than 2 by 2 by 2 is considered noise. That is a standard practice to remove, because data is typically noisy and it's difficult to know when a pore is really a pore or not. So we'd rather remove small features. This also will speed up our subsequent data processing for the demo. So we're removing those, and you will see less segmented here now. We'll see some are removed. So those which are actually, we removed quite a lot here, but this is because the data is downsampled. So it's again something you should do with care. But basically, we've got some pores, the biggest ones, segmented here. And the way to now make a porosity analysis, for example, for pore size distribution analysis, is to make this into we go to connected components, multi-ROI analysis. So we're creating a multi-ROI, which separates each separate item into its own class, and each one can then be having some values calculated. So you can calculate these values here directly, or there's another way to do it using the scalar calculator. Let's just do it by volume here. There's many calculations that are possible. Just a warning, some of these are quite slow. So make sure what you want exactly before you apply it to a very noisy data set, for example. It might take quite some time. But if you select only volume, it's quite fast, as you will see. Now we have, but if you select all, it will be quite slow because it's doing many calculations, for example. Okay, so now we have this. They are still at the moment color-coded randomly. If you click on the bottom here, we've got the multi-ROI highlighted. At scalar information, we want to classify them by volume. So by volume, we have a color map, which is by default this purple to green to yellow color. We can click, let me just show what I did. We can click on this color map, and we can go down to the temperature, for example. I like to use that one more often. And now what we want to do is we want to view the largest pore. So we can sort them here. And if we click on this one here, we can look at center of mass. So I right click on the largest one and look at the center of mass. That is in 2D. It's actually doing it in 2D in all planes. We can see where that pore is exactly. That's quite interesting that pore was not included. The reason for that can be because it's open to the surface. It is open to the surface if you follow that. It's a very long connected pore space open to the surface. So as you can see here, it's the same one here, which is in some way connected to the surface. So it's possible to segment that separately in a different way, but it's open pores are not at the moment included here. Okay, so let's ignore that for now. I just want to demonstrate how to analyze this and to visualize this. In 3D, we'd like to view, let's just make this more transparent. In the new version, as I said before, there's an edge contrast slider, which makes transparency much easier. At the moment, I'm going to try, actually a shortcut way to do it quite nicely, I will show as well, but for now, I'll just show a transparency method here. Oh, and the 3D needs to be activated for the multi-ROI. Okay, so on there's a bit of playing around with the settings here. I think it's the edge contrast which is messing with it. There we go. Okay, so we've got what is a bit of a transparency going on, and we can see the porosity through it. So there's another way of doing that. As I said, in the new version, there's a better transparency function, but in this case, it gives us the opportunity to show meshes. So if we go back to the cube total, you remember that is the entire cube. So we can make a mesh of that. That's quite easy. We go to the segment tab, and when that region of interest is highlighted, it doesn't have to be visible, but when it's highlighted, we can go to create an export to a mesh. So in this case, I'm going to sample it actually, which means it's taking every second point or so, even every third voxel, just because we're only going to use it as a visualization tool. I'm going to click on it to make it white, like that, and we make it visible. So if we put off the data itself, that's what that looks like. Obviously, that can also be smoothed a bit, but we actually only want to view it opaque. It's a nice way of making a transparency so that you see the shadow and of the exterior of the part. So that's quite not taking a lot of memory, or it's quite easy to visualize. All right, so that's how you make a porosity analysis. And now what you can also do is you can, of course, view the volume or pore size distribution, the volume size distribution here. You can change the bin numbers. You can sort this by different features. You can save this picture or save to a CSV file. You can also highlight all of these features and save them to a CSV file directly, not just the histogram data. But what I wanted to show is let's make an analysis using not only, we did a analysis using this function here, we also have a function called scalar generator. So here under basic measurements, the same thing, we can calculate volume, we can calculate surface area voxel wise or with sub-voxel precision using different algorithms. We can also calculate aspect ratio. Let's take the maximum ferrite diameter of these pores, which is the caliper width. Let's do that. We overwrite them. We're happy with that. And so the ferrite diameter is the width of the bounding box, the maximum bounding box width. So it's the longest axis of any pore, irrespective of its dimension. And this is one of the calculations which is quite time consuming, but as the software is being developed continuously, we will have more and more functions. A shortcut method is to take the volume measurement and calculate an effective diameter, assuming pores are spherical, using the definition for volume of a sphere. So I'm not going to wait for that computation here, otherwise the videos take too long, and that's not really the point. All I wanted to show, let's take, for example, not aspect ratio, but let's take another function here, surface area voxel-wise. Okay, close. So we can go into that. Oops. So we need to select what do we want. We want volume. So there we have the volume histogram. And you can change that to surface-wise histogram. And we can also zoom in on that, look at it on a log scale, and so on. So, okay, that's all I wanted to do in this quick video. I think that's a nice demo of objects analysis and how also at the same time some basic segmentation functions. All right.